Sure.
Yeah.
I found a very simple textbook.
Yes.
Which I don't know what you, so it's a textbook on Oxford University Press called Statistical Mechanics, Entropy, Order Parameters, and Complexity. And it's it's a very, it's quite intuitive. So it talks about random walks, the diffusion equation, temperature and equilibrium, phase space dynamics and ergodicity, entropy, free energies, order parameters, and
do you mean the Gibbs free energy, not the free of charge energy?
yes, Gibbs, not free.
Free energy. Yeah, free energy is usable. It's called usable energy. And unlike other dreamers, still they are dreaming free energy from nothing. They generate a machine which costs nothing. Well, so that's why I just point out the free energy is a Gibbs free energy.
Right, I gotcha.
Yeah.
And then the reason I actually found it is because I haven't actually got to this. I haven't gotten to many of these bits, but there's a chapter on correlation, response, and dissipation, and they talk about correlation functions, and then they get into susceptibility and linear response.
Wow, you got everything we discussed. Actually, I was preparing for a talk on the correlation function today. What's a coincidence?
That is a coincidence.
Yes, it's incident. So correlation can be a function, can be discussed in relation to a random process where, or you mentioned a stochastic process, right?
Yep.
And so correlation was introduced, pretty powerful. And actually, some people call it a green function for in the second on some certain in the same context.
Green function.
Green function. The green is the person, not the greenhouse. green is the person. A big name in mathematician is mathematics.
Okay. Yep.
Yes, go on. So what is the purpose you choose this particular textbook to read?
Well, I think what I do with my textbooks is I'll scan the contents and then I'll read the first chapter.
Yes.
And if the language is
the level.
If it's at my level, and I can understand it, and there's a good mixture of mathematics and intuition, then I go, great, maybe I can learn something here. So I just bring it up because I thought it was interesting. And then it talks about, I haven't read this, but susceptibility, dissipation, and the imaginary part. So what we were talking about.
That's complex number. Yes, that's right. Yes. I interrupt you first. The complex number is very play very peculiar role in physics. And at the beginning, people just use the complex number for the convenience to denote to build out the equations. For example, have you studied electricity? For example, in the circuit, if you got a capacitor and inductor, and also resistors, then you have to consider the phase when the current or voltage move across these components. Now, of course, you know Ohm's law. Do you know Ohm's law? Yes.
No, I've heard of it.
Oh, Ohm's law. Oh, okay, probably that's very good. I just cut the story short. So basically, and the people introduce the complex numbers to represent the resistance due to in the presence of capacitor and inductor. So resistance is original idea of resistance only apply for resistor. Okay. Now, how can they manage to put the other two components, which is physically different function, have a different function, into that formalism of the Ohm's law? Then that is where that is use the complex number. So they make the argument that we can rewrite resistance into a complex number, and which is happen to be that very useful, and in order, because that makes the everything, the theory, the basic equation in that in the circuit, they called the RAC circuit. alternate current circuit, more compact. They can actually still trace the phase. Okay, you see, we talked about the phase before. Have we mentioned the phase before? Not yet. No.
A little bit in reference to.
You see the oscillation. You see, you see if the two oscillation oscillate this way, we say in phase. But if they oscillate in this way, they mean out of phase. You see, that is the phase is not a factor. That is not the reason people introduce the complex number. And because I tell you what, so you can decompose, or you can use the Taylor theory to find as far as the amplitude of the perturbation is concerned. Or by the way, we can today spend more time on this perturbation, so that in that context, and we can introduce this correlation function. But I just finished the story that because at that stage when they start engineering, mostly driven by engineering, because they were Tesla and others introduced the AC current. So people have to consider that they have three phases. So basically our current move that way. So every fraction of a second, and then you will change that, you will see the amplitude shift. And so that is why that is a motive to introduce complex number. But it turned out that in modern physics, since quantum mechanics, particularly due to Dirac, Dirac was well trained in engineering, and he knows these tricks to play the complex number, right? Dirac is a great physicist, as good as Newton, because some people think he got a chair Newton used to have. But Dirac was trained as engineering, so therefore he knows how to play with how to use the complex number to get more out of the simple equation. Okay, they can incorporate all variable into a simple equation. That is where the quantum mechanics was unified. Dirac didn't invent the quantum mechanics, but he's so clever. He united two seemingly rivals in quantum mechanics at early days in 1920s. One is called Heisenberg. You know the Heisenberg uncertainty principle.
Yes.
Another Schrödinger. Schrödinger is Austria, who just good at play with differential equation, and that's where he based on the wave idea. So these two early versions of quantum mechanics are exclusive. They cannot mix them up. And Dirac used a complex number to unify these two. Right. Well, that is one story. If you wish, we can talk about this next time.
Okay? Interesting.
And, so anyway, so you can take these keywords here as a takeaway. I say when you use a complex number, you have not just pay attention to the amplitude, but you also pay attention to the phase.
Yes.
Last week we're talking about from a study perspective. If you introduce the complex frequency, and then we can describe the susceptibility from two perspectives, and both outcome will give you equivalent description. Depending on the circumstances, you can choose either of them.
KK.
Yeah, that's KK relation is chronic. It is chronic. So that's why you see the phase become important. And if you just ask the neuroscientists, they have no idea what is the phase, because in their case they just measure the amplitude, right? Any signal from the brain. Actually, I'm creating a short talk with. I have a weekly talk with a neuroscientist in Chile. His English is not very good because he speaks Spanish. So basically, we are trying to work out the commonly concerned issues in the neuron science. So in particular, how to deal with electrical signal. So that's why I learned here at this stage, and they are only focused on the amplitude. the amplitude.
No phase.
No phase.
Mm.
No face. Face.
Yeah, right.
Anyway, so and so you're still interested in thermodynamics or somehow?
Well, it always just keeps coming up, and I think I'm always interested in large populations of things. So I'd love to hear more about the correlation functions and the relation to the perturbations.
Yes, we can discuss these ideas, and I think I prepared this talk a long time ago, but I think we need to do some preparational talk before to actually go to that formula. But I think it's time for us to have a little bit of the chat on this issue, because that will help you to understand the complex system.
Yep.
So after all, the best recipe or toolbox come from the statistics, from physics, right?
I think it does.
There's nothing more reliable or quantitative than the formulas or ideas in physics. So that's why when you study information, you still have to talk about entropy. Entropy is originally come from Kelvin, from the Boltzmann. This kind of the certifications in physics. Okay, and let's go to whiteboard to write these few words before we go. So we'll talk about several things. Share screen. So the context is a perturbation. I can write just a few words here, right? It's more useful, okay? Perturbation. Why perturbation? The perturbation is a small disturbance of external disturbance, by which that the system will respond, okay? And the researchers, investigators take this opportunity to find the behaviors of the system.
By calling it a perturbation, does that mean that it necessarily relaxes?
What do you mean relaxes?
As in, if it's at equilibrium and then there's a perturbation, because a perturbation is small, does this mean?
This is small. This is key. This is small. Small disturbance. Yes.
So it will return eventually to
easily, right?
Easily. Okay.
They don't have to change the dramatic. They don't have to go dramatic change like a reset. Okay. You see, they want shock. The people talking a culture reset. Okay, they just everything from that's terrible. Okay, they want to reset everything like a computer dead. Computer stop. You reset computer. Okay. No, it's not. This is far from perturbation.
Small. Okay.
It actually damages to something. You will damage the system. Okay. So we want to imagine we have a system of interest, and we want to know. We don't know what's going on inside. So, as I will say, the best way is apart from waiting for the. You know that children's story, the rabbit. The hunter saw the rabbit dead under the tree, not by the tree. So he decided to wait there forever, because you see rabbit will come anyway.
I haven't heard the story.
Probably the Chinese saga. So that is just some for describe some lazy people. They just waiting for something happen.
Right.
You can imagine the hunter don't work. They're just waiting for the rabbit to come to ban and die.
Yeah.
Anyway, so for the unknown system, this is our system again. And this system could be simple, could be complex. Okay, depending on the elements. Okay, elements. I can tell what the so-called standard model, although they claim they are dealing with fundamental particles, the elements are quite small, very small. So to some extent, you are not. They should be not part of the study of complex system. Instead, they use a group theory, which is another direction of the mathematical approach in physics, and we're not talking about that. So system. So this is our system. So we got external, apart from waiting what is going to happen, like nuclear decay. We just do something proactive. Okay. Do we use F We use F perturbation. Yeah, we can use F. We got to use perturbation. This, in general, perturbation is a function of time. For example, you can invoke the pulse. Can you see F could be the impulse? Okay. I just, for example, if you just you see something, you just tap, pat. You pat something to see what happened. You see, if you the bee, you see the bee nest. Okay, you just tap whether there's a bee inside. You tap that. Okay, something could happen, right? And two or three bees will fly out, right? That could happen, and you don't destroy it. You don't destroy it. You say, well, from this phenomenon, you say, there must, what conclusion can you obtain? You say, this must be, so that you can see they might be, because inside they might have some tunnels or hole at least in this particular case, right? You see this probably, they got probably internal like that. So that is how you learn something unknown. So you use the perturbation and something happened. Can you see? Something happened. So you say, that is probably, so for example, some two bees fly, okay, come out. You see, this is probably that there must be some tunnel inside. That's how we learn the system. It's called the perturbation, small propagation. Of course, the measurement here is just the UI, right? The detect is just UI. And if we go to more abstract, as we did last time, and this perturbation will give you a response. Do we call the response as observation, right?
Yes,
Use O. So there's, this also must be in general the function of time, right? So in this way, we can gain some information out of this perturbation, out of this proactive approach to study unknown system. Okay. Unfortunately, it's hard to study universe in this way because if you send a signal out, there's no signal come back.
Difficult to measure.
But that just because another reason is that if to study the universe is totally different idea. It's very unfortunate that modern physicists encourage people to go outward instead of inward. You see, I getting old. I from young student getting very old, because during this period of time we learn nothing new about the Earth, about the solar system. Something, sporadically you say, we have seen the fly object near the sun surface, but not of effort, especially at the theoretical levels, spent to study so-called outer space, the model, the universe model. I personally feel it's irrational. It's rational. You see, nowadays, that Elon, what is the guy? The boss of Tesla. And he drew people's attention to the Mars. I think it's ridiculous. Ridiculous, because after all, we haven't got enough understanding, of our Earth. So, for example, what is the internal structure is just the gas at the moment. We talk about the inner core, outer core, the mantle, because that is the terminology where everybody told in the primary school, but nobody knows exactly whether it's true or not. So that is my comment. I perhaps go too far. I have to go back to that equation 1. Okay, equation 1. Do you remember? It's got integral here.
Yeah, with chi.
That is a t. Yeah, this is t. This is chi. This is can we use a tau here? When we have variable to integrate, then we can this is 0 to infinity. We can use a different notation to, even though we don't know that time is variable. And this is how to use the chi, that's the spectroscopy. So in this case, we just incorporate the tau here. Can you see there's a time delay, isn't it? That's interesting, right? So in other words, the response, the suspected may or may not synchronize with the F. Can you see that?
Yes.
Of course, when t equal to, in the particular case, when if you want to synchronize that, you have to consider t equal to 0, except that one. So that is some detail. When you look at the mathematical equation, you have to ask yourself, why did you take this trouble to differentiate that the unsynchronized variable?
Yes.
So it's apparently there's a delay, all right? And you throw a stone into the water, and after a while you hear something. Probably the fish will come out, right?
Yep.
That is a normal. This is how to say, it's common sense. It's still common sense. So this is our equation 1. So this in general, if f is small, so we can emphasize that if f is small, okay, or small or short, small and short, right, and short. So that is a perturbation. Now another idea is that here we have to talk about the some theoretical physics now. We're talking how to describe the system. Okay, this is a system. Now perhaps you're interested in knowing what how do we describe the system? Okay,
I would love to know.
Yeah. So there are two important names in mathematics. Unfortunately, they are all mathematicians, are not physicists. That's the trouble is, okay. One is this guy. So that is how to. That's also that's called the system variable. How to describe system in physics. Are interesting, right?
Very much.
Yeah. So that is the issue, okay? Now in Newton's days, if you just starting from Newton, okay, Newton is still the hero in physics, okay? And in Newton's day, or his series called Newtonians, right? Newtonian. And so we have ideas to describe the object with mass. Perhaps it's moving at a certain velocity, right? And if we know the position of these two vector here, okay, and one, we just have vector before, right? That is a position vector r, and that is a velocity vector v. So if we know that, if we describe this simple system with just one particle here, and then that's it. That is sufficient to describe the system. Do you agree? It's deterministic, and also it's complete description, isn't it? So that is all we want to know. Who needs to know else about point mass? No, we don't. Right? So that is sufficient. So that is mean the system is being fully described. So therefore, in this case, I just draw your attention. We have mentioned two variables. One is r. I can use a vector form. See, so that is r. That's position vector, which normally is function of time and is velocity of time, right? Okay. Now, this is called the coordinate. So there is a position, or this is called the position vector. And that's called the velocity. Okay. Now, eventually we realize that velocity can also be rewritten as I just rewrite the definition, this P and M. Do you agree? You know the P?
Position.
P is the momentum. No, it's momentum. We also can just write the definition that P is a vector just equal to mass times the velocity, right? So what is a P? P is a momentum. Is not the energy. Momentum. Sorry. Momentum. So that is Newton's mechanics all about. And by the way, bear in mind, Newton didn't discuss energy much, right? Although people after him realized that the energy conservation or energy formula can be derived from his famous second law. But for Newton himself, he is not very concerned, not very keen about the idea of energy. Partly because this energy idea is a equivalent idea is introduced by his rival called Leibniz. Leibniz, who claimed he found the calculus before Newton. But we can go to some detail. But today we just draw your attention. Instead of use R and V, we can also use the R and the P to describe this motion. Do you think that? So therefore, that is why. So so in general, people argue that we may just use this the pair, the Q and the Q dot. Can we use the vector here to describe the motion?
And that's just position and momentum.
Yeah, that's what Q dot. Q dot just come from the idea the velocity actually equal to R dot. You see. So if you get right into the component form, that would be the X dot. You see, pi plus. Can you follow me? This is the first derivative. If I use this notation, can you follow me?
Yep.
So the 3D, the vector in the 3D space can be written as this the vector sum. Can you see? Of course, R itself can be written as X and Y. Or if you prefer, as we mentioned before, we can use this X, Y, Z vector form. Can you see? Matrix form. Single column. So this is a single. Just remind some typical terminology we mentioned before. A single column. Okay. Single column vector. So matrix. So single column matrix.
Yeah, just for each dimension in the space.
Yeah, matrix. Yes. So you can see that in Newton's, that's important something to take away, that in Newton's day or in Newton's mechanics or Newtonian mechanics, all right, that's called kinetic. That's the part of kinetic, is foundation of classical mechanics. We can actually describe the motion of the particle by introduce so what is a Q, by the way? Q is a coordinate. So basically, so these they are all called the coordinate, right? Coordinate. So instead of use X, Y, we use the Q. Okay, you can use the Q. You can use the Q, QI. Okay, you can use different Q. So that is for example, I just give you a consistent introduction. So that is called the coordinate. So generally speaking, this coordinate. So you can say X is a Q1, okay, Y is a Q2, and so on and so on. So instead of use X, Y, we use a Q. So in this way, and that is how people eventually who follow the Newtons arguing that we can use the Q and Q dot to represent the particles, right? And these will go to the complex system. If you go to complex system, then you just everything you just put the subscript here. In this way, so we can still consider many body system. So this is a many body system. Can you see? Things getting complicated now.
Many eyes, big eyes.
Yeah, the many body system. Okay. Idea without if this is just a physicist idea, so we just change the coordinate from X, Y to Q. Okay, that is not a big deal. And also, so you can X dot were equivalent to the Q dot, right? Okay, and this Q could be this could be the coordinate. Oh, by the way, we still remember the P. Hang on, I have to remind you. So I probably have to. I will turn to another page because I'm trying to save some space. There's no point. So basically, I just repeat. So basically, in the Newton's ideas, they use the position, right? The position and the P to describe the state. So that's called this. You can call this. This is we can use phi. This wave function doesn't matter. This is just called the state of motion. Okay, it's called a state. state of motion can be described by these a pair of constant. Okay, that's a big deal. That's a state of motion. In quantum mechanics, this is called the the wave function. Function. And but gradually people say, why don't we just the same idea, but we use different notation. We use a Q. Instead of call X, we use a Q and use a P.
And right? And Q dot in this instance still corresponds to momentum.
No, this you're right. You're right. Hang on. I probably will not use this notation. Okay, I just realized. Okay. So in this case, and Q dot is still the velocity. So Q is still velocity.
Okay.
Yeah, yes, Q dot is velocity. Okay, but P dot is slightly different. Okay. Yeah, that's the P dot will be associated with acceleration.
Okay. Yep.
Because if you use a P, right? P will equal to mv, right? Or M equal to mq dot, right? So if you use perhaps I use this way is better. This is more like a differentiation, right? So you got to the the first derivative, isn't it? Not the second derivative. Can you see that?
Yep.
I say square. Okay. So what's that? What's the dp dt? That would be our force. Okay. F for force. That is Newton's law here. So Newton's invented the second law is very useful. He said the force is equal to mass multiply the acceleration. But it also can be written. So this formula can also written as, so if you use if you rewrite the A as dv dt, right?
Yep.
Okay. Then that part, if mass is a constant, then F will be simply equal to dp dt. So that, by the way, that is Newton's second law. This is Newton's second law in different form, right?
Yep. I see. Yeah. Okay. Because the second, first derivative of velocity is acceleration. Yep.
That's right.
Yep.
So that is how at the beginning of the classical physics, classical mechanics. Okay, we use at most we just we introduce a Q. That's all.
Yep.
However, two mathematicians saw the opportunity to show their muscle.
Yep.
Okay, so there are two of them, and I think we mentioned both of them before. And one is this guy. Can you guess? L, start from L.
L. Lagrange and Hamilton.
Yeah, Lagrange. Another is Hamilton. Yes.
Yep.
Newton.
Right? I've been waiting to hear about this for a very long time.
Oh yes, good. Lagrange, and when she got to the ideas, and we prefer use this adjective form called Lagrangian, right?
Yep.
And like Newtonian, and this Hamiltonian. There's Hamiltonian.
Yep.
Hamiltonian. And so actually, this is not just the adjective form of his name, but it also represents a very important quantity to describe the system. So when
I remember when we were doing the maximization.
Yeah. What do you mean by maximization? Did you study the minimization?
Oh, sorry. When we were doing some minimization with the Lagrangian.
Yeah. Least square, least action. You know the least action.
Yeah.
So they have the definition of S. By the way, probably that will be the subject we discuss next time.
Okay.
So actions S can be sent as an integration of Lagrangians and divided by or some kind of volume or path. Yeah, I'm not sure. We'll talk about that. So that is a big deal. That is a big deal of this is called action. So action. But we'll talk about this next time. Today, we just, as introduction, we just mentioned these two names, but also two important quantities to describe the system. In the simple case, the Lagrangian is just the sum of the kinetic energy minus potential energy. You see, something to that's something to energy now. Hamiltonian, by way of contrast, is more close to the total energy. That is the sum of kinetic energy and the potential energy. Of course, these energy are total energy, right? Yep. If you're dealing with many particle, many body system, then you have obviously have to the sum, right? So now we can see, so that was the physics approach, actually mathematics approach. Actually, eventually they just by showing their muscle, and everybody, every modern physicist in 20th centuries follows the Lagrange or Hamilton instead of Isaac Newton, because Newton's idea is great, but they are not as compact or elegant, mathematically speaking.
I see.
But of course, we just consider this system. We just consider mechanical system. Okay, be careful. We have in physics, we divide nature into different type of system. One is a mechanical system. So this is this is called the mechanical system. Mechanical. Mechanic. When we study mechanical system, we can just consider that the things, object to be studied is made by different elements, right? This is 1, 2, 3, 4, okay? And this particle may have the kinetic energy like a particle. It's just not like a gas. Can we imagine this as a gas? Of course, gas is a complex system, right?
Yes.
And people didn't realize because it's got Avogadro number of atoms. There's no way you can actually start individual particle in the gas. That is the idea of the statistics come from, or originated. Sorry, rather its origin of statistical physics. Or they still call it mechanics. That's why traditionally in the textbook we still refer it as statistical mechanics.
Yes.
So you can imagine. So this has, and each of them they may have the interaction. Can you see? They got interaction. And in interaction, because of interaction, that is the origin of the potential energy. Okay. For example, everybody, when you jump, where you have to bump backward, because why? Because the potential energy increase, which is not stable. So that's why you don't have torque. By the way, that is something very. This is a paradigm shift, right? Paradigm. Do you call it paradigm shift? It's paradigm shift. And in Newton's mechanics, we can pinpoint the force. Okay, you see, because you threw the basketball up, and the basketball eventually fall down. Why?
Gravity.
Gravity fall. It falls, right? Now you have to change your mind. You have to reset your mind. Forget about the force. Let's talk about energy. So the energy of the basketball, and when they go higher, so the energy is higher. So we ask a different question: is that mechanically stable?
I see. No.
No. Yes.
No.
What would happen with what would be safe? What would be more stable? More stable when the potential energy increase or decrease?
Decrease.
Yes, common sense, right?
Yes.
So that is why this is called the minimum. So this is the minimum action. So basically, they are looking for somewhere, and that we got the most stable position. Can you see that?
Yes.
So you can do all these paths. This is integral here. So however, relatively speaking, only one position is stable, which is that's minimum. So the action is S go to the minimum. Go to the minimum.
Yep.
So that is a pretty paradigm shift, okay?
Yes, force to energy. Okay.
No. We don't have to consider force. No force.
No, that's right. Sorry, force. No force moving to energy.
Energy. So we're talking about energy now. Yep. So the idea of this tradition, this shift, a paradigm shift, is that we introduce that's from the force.
Yeah.
We can define to the energy. All right.
Yeah.
That is a paradigm shift in mechanics, in physics.
Mm-hmm.
Energy. And which actually that is also the origin of many troubles encountered in modern physics.
Yep.
Because they have, by choosing this description, so basically, so this is described, so both L, so you can this is called the system, can we put a legal name for that? This is, this, can we call that? Yeah. So this would be called the system describer.
Mm-hmm.
Describer.
Is the Hamiltonian kinetic minus potential or kinetic plus potential?
Oh, plus, you are correct. Thank you. Yes. That is why in quantum mechanics, for time being, when we're dealing with a particle, single particle, say electron in atom, we still use Hamiltonian. So the Schrödinger equation dealing with Hamiltonian, okay? Heisenberg's mechanics dealing with the Hamiltonian.
Mm-hmm.
And the Dirac's unified mechanics also dealing with Hamiltonian. Okay. And that is a little bit, this is a bit of the, how to say, that is a little bit, in my opinion, that is logic, because people don't want to go too far from something abstract to describe a system.
Yeah.
What is the difference between energy, kinetic energy, potential energy? It's energy difference, right? Mm-hmm. It doesn't make much sense. Okay, yeah. Sometimes the total kinetic energy is greater than potential energy. Others, the kinetic energy is smaller than potential energy. Mm. And so, in terms of the using a proper system describer, I would prefer, or as a student or the beginner would prefer to use Hamiltonian, because that makes sense. We are dealing with the system, and if we know the total energy, then we can describe the system. That makes sense. Do you agree?
It's intuitive.
Yeah. How can you say the difference between kinetic energy and the potential energy allowed you to describe the system? I should put the first question mark in the first place. Okay. Mm-hmm. Yeah. But of course, that's something ironic in or something strange in when you combine the physics idea with mathematical thinking or formalism. Okay. Yeah. And in history, both Lagrange and Hamilton made their contribution. They really show the world that they can describe the multi-body system. They don't call complex system, because those people who advocate the complex system today haven't born yet. They just call it a multi-body system, okay? Yep, okay. Multi-body system.
Yep.
So basically, we got a system describer. We still have external. We have external perturbation, right? Or could be perturbation, and we can observe. Yep. The same thing. So this idea is still applied. You got more importantly that we have to understand the two formalism, namely the Lagrangian and actually they call Lagrangian mechanics and the Hamiltonian mechanics. Yep. And two of these mathematical oriented formalism for mechanics allow the people to have a short note of very complicated system. Okay. For example, I give you an example. For example, the kinetic energy. How can we write the kinetic energy? Can you think? This is total. If you have, say, n particle, we've got n particle, probably is capital N.
Oh yeah.
N particle. Yeah. How can we denote this total kinetic energy?
So the sum of
like sigma, right?
Sigma,
yes. With half. No, half. Well, you know the kinetic energy, single kinetic energy. Do you remember? There's a half v squared.
Oh yeah.
So that's v squared.
Yes. Okay.
And it also can be rewritten as a p squared divided by 2m. Can you follow me?
Yep.
So basically, P is by definition equal to the M multiplied V. So if you do this substitution, so kinetic energy can be written in terms of the P. Okay.
P squared over 2M. Yep.
Yes. So can we use P? Can we use P?
Yes.
So we can we just for time being we just use this VI squared, and eventually we switch to this I from 1 to N. Okay.
Yep.
So that will give us, we could put this we put the P. We put half here, and that is Mi. So each particular Mi, and that would be a P squared. Can you say Pi squared?
Yep.
And I from 1 to N, isn't it?
Yes. Just by substitution. Yep.
That's it. Yep. So that is how to describe the part of the system by consider the kinetic energy. Okay. And of course, this is consistent with atomic theory in physics. Okay. And this is actually just from different approach, and people gradually accept that the ancient Greek philosophy named the Democritus. You know Democritus? That is the person. Democritus.
I assume he was he was keen on democracy.
Yeah, how to say Democritus?
Yep.
That is atom. So that is origin of atom, or father or grandfather of atom. So atom theory, theory, element.
Yep.
So basically, by introducing or applying the Lagrangian and Hamiltonian mechanics, and we are getting closer to the atomic theory, because in theory, any complex system can be divided into atoms. Do you agree? It could be atmosphere, it could be neuron, you could be can you imagine other complex? The birds, you see the flying formation of millions of birds during another picture, they have flying formation as a whole. And many I noticed from this YouTubes and many lectures who are not physicists always use this a shorter video to get draw people's attention. Look, we are studying this type of complex system. We are trying to find this kind of simple rule governing the motion. But that, again, that is indeed that birds flying formation can be perfectly described by both Lagrangian and Hamiltonian. Each bird were treated as object, element.
Is that to say any system in principle can be described in principle
mechanical. So because here, why it's mechanical, then we have mentioned the potential part, potential energy part. The potential energy part is a bit tricky because you can, in those days, the only known force is Newton's contribution. So that is gravitational law, universal gravitational. So that's why this is a mechanical system, okay? We can, so both Lagrangian and Hamiltonian mechanics were introduced in the context of mechanics, in which two mathematicians trying to make the Newton's description more compact, more general. Okay, but there's a paradigm shift. That is something to take away. They don't talk about the force anymore. They talk about energy. Energy. So gravitational law tell us that in those days, the only there's called a universal. It's called a universal. Big deal. Universal. Actually, some that neuroscientist in Chile asked me. So he said, I feel surprised. We repeatedly encounter some, the basic physical laws governing the phenomena in the brain. I say I'm not surprised because the physicists are looking for the natural law. So how can you be so surprised? So of course that is a universal gravitational is surprise. It's governing everything, no matter how small it is. That is a force. Actually, as a force between I and J can be written as a constant multiply mass I and mass multiply mass J divided by their distance I and J. So that is actually the formula for the.
So there's a tight conceptual link between gravitation, interaction, and potential energy.
The potential, the origin of potential energy is due to the interaction among between the two particles. Okay. Any pair will satisfy. Can you see this dot here? So yep. In this case, of course, if you're dealing with gas and the situation is more complicated, okay, probably is not a good way to describe this as gas, because when we're dealing with gas, we have to consider electromagnetic interaction. So it's not very good ideas, but basically the potential, by the way, the potential energy can be described in several times. So the potential energy is due to elastic. For example, if the two object is connected by a spring, right, with constant K, it's not Boltzmann constant. So they will have the elastic. You got elastic. They call it elastic. So it's like a spring. Can you get spring? Yep. Elastic potential energy, and also gravitational. So basically, they have two types of gravitation. So you can use this sum to describe that. For the elastic one, is relatively simple. If you just consider this is the mass on both sides. This is Mi, is Mj, right? So therefore, you just consider this is the kinetic energy and the extension from the original. So this EP will be equal to, you got the sigma here, be careful. So you got just you can half here and a spring constant. And in this case, we just assume the spring constant is the same, okay? Yep. Between the pink. If make it more general, the K could be different, then the formula will be more different. But in this case, we just consider that would be the case as I and J, okay? So in this way, when you do summation, you have used this notation. So I not equal to J to N. Do you know why? No. This is elastic. Because the potential energy comes from a pair of different elements. Yep. You cannot have self potential
interaction. Yeah.
Just one, okay? Now, if you pay attention to that, and eventually you notice that these, when you move to the modern physics, and they just massage these ideas, okay? They just mix them up, okay? Just play, just like make the braid, you see, you make the flower together. So they still talk about potential energy of a single electron. That is something. I'm going to do some research on this aspect this year. I'm doing the research on electricity this year. So that I'll tell you something interesting when we have something, when I have found something exciting.
Good.
And so that is why how to denote the elastic one. Now, similarly, how do we just bear in mind the potential energy also can be written as in the same way, but slightly different. Can you write down here? We still have some space here. So the gravitational potential energy is the total, right? You have to do the sum. And that energy is determined by the gravitational constant and the two mass, so mass M and mass J, but is R is just Ij, no square. So that is the formula. So if you put if that is attraction, you have put a negative sign here.
Yep.
Okay. Yep. So we got some formula here now. So basically, we have if you're looking for the Lagrange, that we're equal to. Can we write the many particle system now? Yep. That is one is a kinetic energy. So that is a half. That is a half. We can put half outside sigma if you wish, as a half. That is the mass I. Okay. And the Pi, right? Sorry, I have to write another form. Sorry, I write this form. There's a Pi square and 2Mi. So better to change that moment.
And that's equal to pi.
Not yet. This is kinetic. This is kinetic. I just clean this one. I make some mistake here. So I put the 2 inside. Okay.
Yep.
Okay. So that will be the summation will be I equal to 1 to n.
Yep.
Okay. Number of the elements. Then you have the minus potential energy. Okay. Potential energy. So inelastic one. So that inelastic one. That will be equal to, in this case, you got gravitational constant. So mi, mg between the 2 objects. Okay? And that will be the, because you minus, that becomes sum. Okay, so you have minus negative. Minus negative, yeah. Because it's because attraction. For attraction, the potential energy is negative. When you do summation, you can check every I and j except I equal to j.
Okay, yep, because you can't do yourself.
That is notation. So every time I provide some formula for you, all right?
Yeah.
You can have a close look. Now, if of course, if that involves the inelastic potential energy, then you have to put an additional. This time is minus because the Lagrangians, the difference between kinetic energy and potential energy. So that would be the sigma. Sigma, that is half, that is k, and we just assume k is the same everywhere. And we don't. If we don't, we can also make sure that we can do summation of the k. You see, that's the trouble. See, we got IJK, but we got the K here, so a little bit not consistent. That is a concern for mathematician, you see. So what in order to make a consistent result, I prefer to use this Hooke's law. Can we use the H here as constant?
Okay.
It's K here. Okay. So that is one of the object which has I can use I. Okay. Yes, I can use I. Oh, IG. Sorry, IG. IG. Oh, that makes sense now. That makes sense now. So we still use K. Sorry, we still can use K. You see that you are watching how physicists are doing the formulation, right?
Yeah.
They want to make this looks more compact. So I still use the K for constant, and the distance between them will be Rij. And square, okay, and this summation is I is not equal to j to n.
Yep.
Okay, I give you a chance. How to write the Hamiltonian, please? It's a simple exercise. Yes.
We just need to change it to a plus.
Yes, please. Yeah.
Yep. So we're going to.
Can you copy them to make some sense, make some feeling? What's there?
Yeah, so we've got Hamiltonian equals the sum of from 1 to n of.
You can. Do you have pen or not?
Yeah, I haven't logged in yet. Let me.
Okay, doesn't matter.
So basically, the only difference is going to be that it will be a plus the gravitational term.
That's right. The second becomes minus, right?
Yeah.
The same and certain become plus. Can you see?
Yes, exactly.
So that is how to build the system describer.
Yes.
And it is a describer. And there are many related terminology follows this notation. For example, if you use Lagrangian divided the volume, okay, then you got the Lagrangian density. That's something very bizarre idea. Then people still use that idea in modern physics because Lagrangian density, right? Okay, it's
abstract.
Abstract, yeah. Well, but it's people, and this is okay. If you have a Hamiltonian divided the volume of the system, what do you get?
Just energy per
energy density. It's just energy, yeah. Right? Okay, that makes sense, right?
Yep.
But that is also the trouble, the origin of trouble, because in both the two mechanical physics, we are dealing with a mechanical system. How unfortunately, these two ideas, both Lagrangian density and energy density, has been applied when we started quantum mechanics of the electromagnetic field. magnetic field, electromagnetic field is invisible, right? No mass, no mass, no charge.
Yep.
Anyway, this is just some extension for you to understand that today we have learned several terminology. Yes.
Yes.
Okay. So whenever next time people talk, oh, we are dealing with Lagrangian density, say, I know, it's just air divided by volume. Okay. All right.
Yes.
Okay. I hope.
Awesome.
Well, time flies. But we eventually move to the coronation next time. All right.
Okay, that sounds great. I look forward to it. This has been such a great lesson. Thank you very much.
Thank you. I will save this one. Since that.
Oh yeah, awesome.
Okay. Goodbye.
I'll speak to you next week. Bye, Dr.
Okay.
Young.
Goodbye.
Yeah.